Amidst the vast expanse of the open sea, a colossal fortress silently looms above the waves, the USS Nimitz, a nuclear-powered aircraft carrier that weighs in at around 100,000 tons. Its sheer size is staggering, dwarfing everything from container ships to naval destroyers. Yet, this floating behemoth is equipped with a powerful tool that has long puzzled spectators and engineers alike, the steam catapult. When an aircraft prepares for takeoff, the catapult's colossal pistons engage, unleashing a torrent of high-pressure steam. In mere seconds, a 36-ton fighter jet is thrust from 0 to 165 knots, achieving a velocity that can only be described as breathtaking. But here lies the enigma: why does an aircraft carrier, fueled by nuclear reactors, rely on steam to launch its planes? As we dive deeper into the mechanics of this astonishing system, we must confront a fundamental question: what makes steam the medium of choice for catapult systems on these floating giants? This inquiry will unravel a tapestry of innovation, physics, and engineering decisions buried within layers of history and practicality. The essence of an aircraft catapult lies in its ability to rapidly accelerate a heavy aircraft down a short runway. For perspective, consider this: a traditional aircraft carrier would require a runway nearly a mile long for takeoff if it relied solely on standard takeoff procedures. This requirement is impractical when the vessel itself is designed to operate mainly at sea. Instead, the steam catapult provides a solution. At the heart of its operation is an accumulator, which acts as a reservoir for the high-pressure steam created in ships' reactors, an innovative choice that demonstrates the brilliance of energy storage and release. The Nimitz-class carriers utilize a system of accumulator cylinders that can store this steam at pressures reaching over 600 pounds per square inch. This stored energy is harnessed when flight operations dictate, releasing the steam in a controlled explosion through a hydraulic piston. This piston, often likened to an oversized brake lever dragging a massive aircraft downhill, catapults the plane across a 100-meter track before it takes flight. During this brief moment of launch, roughly 95 megawatts of power is delivered, an extraordinary figure that can illuminate a small city. The physics behind the acceleration of the aircraft is just as breathtaking. The piston moves the aircraft rapidly, transforming potential energy stored in the steam into kinetic energy. This allows the jet to reach its takeoff speed in mere 2 seconds. To truly appreciate this, visualize the rapid acceleration felt when a sports car goes from 0 to 60 miles per hour in just a few seconds. Now imagine this experience multiplied by a factor of 5, as a 36-ton aircraft is hurled into the sky with a force that pushes the limits of physics. The Nimitz-class, the largest class of aircraft carriers ever built, employs this potent steam catapult technology due in part to its heritage. The development of this particular system dates back to the mid-20th century. As naval aviation expanded, engineers grappled with the need for rapid launch capabilities from ships without extensive flight decks. The concept of harnessing steam from the reactors was revolutionary. Aboard these floating cities, the reactor does not merely power the ship, it also facilitates advanced operations. The choice of steam is crucial: heat energy can be efficiently converted into mechanical work. Conversely, many might assume that the more modern approach would favor electrical catapults powered by electromagnetic systems. After all, the system used on the USS Gerald R. Ford represents an evolutionary leap in aircraft launching technology. These electromagnetic launch systems require less maintenance and eliminate the risk of scalding steam. Furthermore, the significant advancements in electric propulsion have made this technology attractive for future systems. However, the transition has not been seamless, with delays and challenges leading to questions about whether electromagnetic systems can fully replace steam. While there is merit to these innovations, a critical reality remains: tradition and tested technology have sustained the Nimitz-class fleet. The reliability of the steam catapult has proven itself time and again through extensive use in real-world conditions. The engineering community often talks about reliability in terms of failure rates and longevity. There have been more than 20 million successful catapult launches in the history of U.S. naval aviation. The engineering triumph here, however, lies not solely in the catapult's mechanics, but rather in its integration into a larger system of naval operations, maintaining both speed and safety. If you were on deck as an aircraft prepares to launch, you would witness an intricate ballet of precision and coordination. As each plane is positioned and flight crews work in synchrony, the anticipation grows. With all systems go, the catapult operator initiates the pressurization sequence, imbuing the piston with energy. In those heart-stopping seconds, everything aligns. The pilots draw breath, the crew braces, and then, the mechanics hum to life as the pilot pulls back, ready for the thrust. It's then that the launch mechanism springs into action. Think for a moment about the sheer power generated when a 36-ton jet is propelled over 100 meters in the snap of a finger. In laying the groundwork for this launch, engineers ensure that the catapult is set for optimal operation, every pressure reading, every steam release optimal for peak performance. Yet, paradoxically, while the Nimitz-class ships utilize steam with remarkable proficiency, a common misconception persists: the false belief that only hydraulic systems could effectively accelerate such massive weights. In reality, steam offers unique characteristics that hydraulic systems cannot replicate effectively within the parameters defined by naval flight operations. Simply put, it is not merely about power output, it is about efficient energy transfer in extremely short bursts. Where hydraulic systems might be hamstrung by weight and maintenance requirements, steam catapults capitalize on the heated gases existing in the carrier's ecosystem. To put it into perspective, consider how water boils in a kettle. When adequately heated, the steam generated can lift a lid, but just imagine scaling this up to the size of a house. This dramatic increase sensitizes the engineering potential harnessed aboard an aircraft carrier. In engineering, scaling often leads to exponential results, and thus, as the units grow larger, so too do the capabilities of the systems. And so, the design of the Nimitz-class catapult system substantiates the fusion of legacy and innovation. While engineers continually seek new methods to optimize launching capabilities, the realization remains that within existing frameworks, there exists a wealth of potential still untapped. As we take a moment to reflect on this engineering marvel, it becomes evident that every impressive feat of technology arises from layers of complexity that ultimately coalesce into an efficient solution. This intersection of physics and engineering elicits a sense of profound admiration for the intellect and resourcefulness of those who design and build these machines. In examining the steam catapults of the Nimitz-class carriers, we can see the invisible engineering that surrounds us every day: reliable, practical, and timeless solutions found in unexpected places. In our quest for understanding, we uncover a world of ingenuity that shapes our modern existence. Every giant machine hides one piece of engineering nobody notices. Subscribe for the next one, and tell me below which machine you want taken apart. As we delve deeper into the mechanics of steam catapults, there's a critical step that merits further exploration: the role of the accumulator cylinders in this intricate system. These cylinders, resembling giant steel barrels, act as the heart of the catapult mechanism. Each accumulator can hold steam at a pressure exceeding 600 pounds per square inch, enough to power the entire launching operation of an aircraft in an instant. This high-pressure steam is generated continuously by the ship's nuclear reactors, which operate at temperatures reaching upwards of 600 degrees Fahrenheit. The integration of these reactors into the launch system embodies a remarkable synergy between naval propulsion and flight operations. Take a moment to picture this scene: the aircraft floats on the flight deck, poised for takeoff, reinforced by the stellar engineering of its landing gear and fuselage. When activated, the catapult operator sends a signal, initiating the process that fills the accumulator with steam. This operation underscores an essential aspect of nuclear-powered naval vessels: their ability to produce vast amounts of steam energy for multiple uses, far beyond propulsion. This is the essence of versatility in advanced engineering. As the aircraft is secured, the hydraulic release valve of the accumulator is opened. A surge of steam rushes towards the catapult, activating a series of pistons that propel the aircraft forward. The force of this launch must be seen to be believed. The sheer energy would be comparable to launching a small car off a cliff. In essence, the pistons function like the massive arms of a slingshot. They convert the accumulated steam pressure into rapid kinetic energy, accelerating the 36-ton frame down the sleek track with mind-boggling quickness. For illustrative purposes, let us examine a specific instance in naval history, the launch of a Grumman F-14 Tomcat from the USS Nimitz. On that particular day, amidst the roar of engines and frantic activity on the deck, the F-14 was strapped into position, waiting for the decisive moment. As the launch sequence began, the tension was palpable. The energy buildup was instant and explosive, driving home the realization that the catapult's operation is a fine-tuned interplay between pressure, steam, and timing. The aircraft blasted off, reaching its speed of 165 knots in mere seconds, the pilot experiencing forces that would feel like being strapped to a rocket. This example highlights not only the power of the catapult but also the significant human factors at play. The personnel responsible for these launches undergo extensive training, particularly in handling the rapid and intricate procedures involved in operating the steam catapult. Each launch requires discipline, precise timing, and keen awareness of the environmental conditions, such as wind direction and speed, which can influence the thrust of the aircraft. Facing down the threats and demands of the unpredictable sea, these engineers and pilots embody the spirit of naval aviation. In the world of heavy machinery, engineers frequently confront the dark shadows of mechanical failure. The challenge of catapult launching is no different. The mechanisms behind steam catapults are robust, with fail-safes integrated into the system. However, incidents can occur. Take into account the experience of the USS Dwight D. Eisenhower, where a catapult malfunction during flight operations caused a brief disruption. The quick responsiveness of the crew, combined with an understanding of the catapult's workings, resulted in minimal downtime despite the substantial technical complexities involved. After thorough investigation and adjustment, these kinks were resolved, solidifying the credibility of the steam catapult technology. Now, while the steam catapult has proven reliable, it's important not to overlook the alternative methods that have emerged alongside it. As mentioned earlier, the introduction of electromagnetic launch systems showcases a modern approach to solving challenges of aircraft launching. These systems utilize powerful electromagnets to accelerate the aircraft, offering some advantages over steam technology. For instance, with electromagnetic systems, the mechanical wear on components is significantly reduced because of the absence of physical impact when launching aircraft. However, they bring their own set of complexities, including the need for powerful electrical sources and intricate control systems. At this juncture, the debate of which method is superior still rages in engineering circles. Despite being at loggerheads with newer technologies, the steam catapult has several advantages that position it as a stalwart in aircraft launch systems. One such key element is its capacity to provide consistent launch speeds. Many pilots swear by the precision and reliability of the steam catapults, emphasizing the predictability in their launches, critical for high-stakes naval operations. That said, the engineering world is thus faced with a paradox. While progress aims to improve safety and efficiency, such as minimizing the risks associated with steam and pressure, the dependability of the traditional steam catapult remains unparalleled. Let's consider the historical context behind this technology. The steam catapult has roots tracing back to the development of powered flight and was significantly advanced during the 1950s with the advent of jet technology. Ships such as the USS Forrestal introduced steam catapults into their design and operational philosophy. Its development was not merely a function of technological advancement, it was a necessary response to the evolving nature of aerial warfare. The weight of aircraft grew heavier, and their performance demands increased, establishing steam catapults as essential devices for ensuring mission readiness. Over the decades, these systems underwent iterative improvements, learning from the challenges faced during their operational lifetime. Technologies were refined for robustness, scalability, and efficiency, leading to the systems we recognize today. In modern times, the steam catapults of Nimitz-class carriers represent nearly 70 years of evolution in naval engineering. Yet, the future holds promise as newer generation aircraft carriers enter the fray. With prototypes like those proposed for the USS John F. Kennedy embodying both steam and electromagnetic systems, the question remains, what does the future of aircraft launch technology hold? It's probable that we will see a convergence of both methods, taking advantage of steam's reliability while also leveraging the efficiency of electromagnetic systems to meet the demands of future aviation. As we draw closer to the conclusion of our exploration, let us reflect on the duality of innovation, the coexistence of established methods, such as steam, alongside new age solutions. The world of engineering is one rich with lessons from history and potential for future advancements. When exploring a vessel as monumental as the USS Nimitz, we grasp a sense of monumental legacy, an intricate ballet of creativity and problem-solving that has propelled the United States Navy into the forefront of aviation warfare. Ultimately, every sailing flight deck aboard these carriers is a testament to the meticulous convergence of harsh realities faced in engineering, operation, and human factors. Behind every successful launch lies countless hours of engineering calculations, real-world testing, and robust training procedures, to meld the reliable with the innovative. Thus, the steam catapult's distinctive niche continues to survive, propelled by those who recognize both its historical significance and its ongoing relevance in military endeavors. As we pause to appreciate the beauty of such ingenious engineering, we discover it interlinks seamlessly with the pursuit of solutions. Every intricate mechanism and decision serves as a thread in the vast tapestry of human knowledge and creativity. What appears mundane at first glance, the skillful manipulation of steam, transforms into a powerful reminder of human ingenuity. Every giant machine hides one piece of